Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 3, Section 1, Chapter 4, Topic 3. Understanding thermal resistance categories in semiconductor packaging: conduction, convection, and radiation. Introduction. In the intricate domain of semiconductor packaging, effective heat management is vital for maintaining device reliability and performance. Thermal resistance, a key parameter in thermal analysis, characterizes the resistance to heat transfer through different mechanisms: conduction, convection, and radiation. Categorizing thermal resistance based on these mechanisms provides a comprehensive understanding of heat dissipation in semiconductor packages. This overview delves into the categorization of thermal resistance for conduction, convection, and radiation, elucidating their significance and implications in semiconductor packaging. Conduction thermal resistance. Conduction thermal resistance arises from the resistance to heat transfer through solid materials, such as package substrates, die-attach materials, and interconnects. It depends primarily on the thermal conductivity of the material and the thickness of the medium through which heat is conducted. Conduction thermal resistance, Rcond, can be calculated using Fourier's law of heat conduction. Rcond equals L K dot operator A, where Rcond is the conduction thermal resistance, degree C, W. L is the thickness of the material, m. K is the thermal conductivity of the material, W per meter K. A is the cross-sectional area of heat flow, m squared. Conduction thermal resistance is crucial for understanding heat transfer within semiconductor packages and optimizing material selection and package design to minimize thermal resistance. Convection thermal resistance. Convection thermal resistance arises from the resistance to heat transfer between a solid surface and a fluid medium, liquid or gas, through convection. It depends on factors such as fluid velocity, fluid properties, surface geometry, and temperature differentials. Convection thermal resistance, Rcond, is influenced by the convective heat transfer coefficient, HH, which represents the effectiveness of heat transfer between the surface and the fluid. The relationship between convection thermal resistance and convective heat transfer coefficient is given by Newton's law of cooling. Rcond equals 1 per hour. Operator A, where Rcond is the convection thermal resistance, degree C, W. HH is the convective heat transfer coefficient, W per square meter K. A is the surface area of heat transfer, m squared. Convection thermal resistance plays a significant role in semiconductor packaging, particularly in applications where forced or natural convection is employed for heat dissipation. Radiation thermal resistance. Radiation thermal resistance arises from the resistance to heat transfer through electromagnetic waves, primarily in the form of infrared radiation. It depends on factors such as surface emissivity, temperature differentials, and surface areas involved. Radiation thermal resistance, RAD, is influenced by the Stefan-Boltzmann law, which quantifies the radiant energy emitted by a surface per unit area per unit time. RAD equals 1 epsilon dot operator sigma dot operator A dot operator T1 to the power of 2 plus T2 to the power of 2 dot operator T1 plus T2, where RAD is the radiation thermal resistance, degree C, W. Epsilon is the surface emissivity. Sigma is the Stefan-Boltzmann constant, 5.67 times 10 carat minus 8 W per square meter K. 45.67 times 10 carat minus 8 W per square meter K carat 4. A is the surface area of heat transfer, m squared. T1 and T2 are the absolute temperatures of the two surfaces, K. Radiation thermal resistance is significant in semiconductor packaging, particularly in applications where direct contact between surfaces is limited, such as in vacuum environments or when insulating materials are present. Implications and optimization strategies. Understanding the categorization of thermal resistance for conduction, convection, and radiation is essential for optimizing thermal management strategies in semiconductor packaging. Material selection. By considering the thermal conductivity of materials for conduction, convective heat transfer coefficients for convection, and surface emissivity for radiation, engineers can choose materials that minimize thermal resistance and maximize heat transfer efficiency. Package design optimization. Optimizing package design, such as increasing surface area for convection, enhancing material thickness for conduction, and improving surface properties for radiation, can minimize thermal resistance and enhance heat dissipation capabilities. Thermal interface enhancement. Improving thermal interfaces between semiconductor components and heat sinks can reduce interface resistance and enhance heat transfer efficiency, particularly for convection and radiation heat transfer mechanisms. Conclusion: categorizing thermal resistance for conduction, convection, and radiation provides a comprehensive framework for understanding heat transfer mechanisms in semiconductor packaging. By optimizing material selection, package design, and thermal interfaces, engineers can minimize thermal resistance and enhance heat dissipation efficiency, ensuring the reliability and performance of electronic devices in diverse applications. As semiconductor technology continues to advance, mastering thermal resistance categorization remains essential for addressing the evolving challenges of heat management in semiconductor packaging. Thanks for watching. Please like, share, and subscribe.